All right, what we're going to do in this video is explain how scientists determine the enthalpy or the heat of the reaction. So what the delta H of the reaction value actually is. Okay, yeah, you can look stuff up, but how did they actually figure that out? Well, they use something called Hess's Law. And Hess's law is where you use the overall enthalpy change in the reaction, and that is determined by putting together the individual steps of the process. And the key to understand this is to understand that two things happen when a reaction happens or occurs. The reactants have to break their bonds and the products have to make their bonds. So if you know your formation values, okay, your delta H's of formation, you can break some of the stuff that's formed and you can make some of the stuff that is formed in order to figure out what your delta H of the reaction is going to be. So what we are going to do is we are going to work through a proof of Hess's law, and then the next video is going to show you the shortcut. So the proof is going to be to determine how we know what the delta H value is for this chemical reaction here. So PbCl2 and Cl2 are going to combine to make PbCl4. So we need to do a couple of things. Number one, we need to figure out how much energy it takes to make PbCl2. Number two, we need to figure out how much energy it takes to make Cl2. And number three, we need to figure out how much energy it takes to make PbCl4. Well, PbCl2 I can look up, and that is going to be our negative 359.4 kilojoules per mole. And the heat of formation equation from its reactions is Pb plus Cl2 makes PbCl2. So that's how much energy it takes to make PbCl2, to form it. Okay? Chlorine is 0 because it's an element, so duh, it already exists because like nature and science and stuff. And number three, the heat of formation for PbCl4 is negative 329.2 kilojoules per mole. Its heat of formation reaction is going to be Pb plus 2Cl2 to make PbCl4. So what I am doing with the Hess's law proof is I am arranging these two equations so that when I add them together, my net reaction is going to be the same as what was initially there. It's like a proof that you see in geometry class. So instead of making PbCl2 because it is a reactant, I'm actually going to break it. So I'm going to take this reaction and I'm going to flip it and reverse it. Yep, like Missy Elliott says, flip it and reverse it. All right, and I am going to make PbCl4. So that means that I'm going to leave it this way because it is actually forming it. So if I flip this reaction and I add this reaction together, I should get the net reaction that is the same. So if I do the same thing to the values for your delta H, for your heats of formation, I should get the overall enthalpy of the reaction. All right, so let's do exactly that. All right, PbCl2 and Cl2 make PbCl4. So first things first, I'm going to write my heat of formation equation for PbCl2. So that is Pb plus Cl2 makes PbCl2. All right, but I am going to flip this because I am not going to make PbCl2, I am going to break it apart. So instead, I'm going to do this. PbCl2 breaks up into Pb plus Cl2. So if my delta H value, my delta H of formation for this is going to be our negative 359.4 kilojoules per mole, I'm going to flip the value over here. So my delta H value for this is going to be positive 359.4 kilojoules. All right, next I have my formation of Cl2. Well, that's already made, so I don't have to worry about him. And then I'm going to make PbCl4. So Pb plus 2Cl2 makes PbCl4. And its delta H of formation is going to be negative 329.2 kilojoules. Well, since this one is fine, I'm just going to write it over here in the exact same way. Pb plus 2Cl2 yields PbCl4. And my delta H value, I leave it just the way it is, negative 329.2 kilojoules. So what do I do with these two values? I am going to add them together. And I get PbCl2 from the first one plus Pb plus 2Cl2 yields, on the right side, these three things. Pb plus Cl2 plus PbCl4. All right, then ask yourself, what cancels out? Okay, well, I have a Pb on the left and a Pb on the right, so I'm going to cancel them out. I have two Cl2s on the left and a Cl2 on the right, so I'm going to cancel out this one, and this one becomes 1. So my net equation is PbCl2 plus Cl2 yields PbCl4. Did I get the same reaction? Does this reaction match this reaction? Yes. So if I can flip these equations and add them up to get my net reaction, I can flip their heat of formation equations, add them together, and get the delta H of the reaction. So what is 359.4 kilojoules plus negative 329.4 kilojoules? Well, that is a grand total of 30.2 kilojoules per mole. So this is an endothermic reaction, and that is going to be the proof on how they can figure out how much energy this reaction will require. Okay, so to run through that again, you take your reaction, okay, any of your reactants you are breaking, so reactants need to get flipped, okay? Oops, come on, pen. Your reactants must get flipped. And when they get flipped, this value right here changes to a positive value, or if it's positive, then it would change to a negative. Okay, you don't need anything for the chlorine because you are just simply adding that together, and then you leave your reactants and show that you are forming your PbCl4. So what you do is you add those two together, you get this whole reaction, you simplify by crossing out the Pb and the Cl's, so you get one of them. You see that that matches your original reaction, so you should be able to flip the delta H's in order to figure out the overall enthalpy of the reaction as well. Okay, another example is going to be what the heat of the reaction would be for the decomposition of calcium carbonate when it's heated. Okay, so we have calcium carbonate, calcium oxide, and CO2. So I'm going to write the heat of formation equations for each one. Okay, so I have Ca plus C plus 3 halves O2, making CaCO3. The delta H of formation value is going to be negative 1207 kilojoules per mole. CaO would be Ca plus half of an O2, making CaO, calcium oxide, and I would look up on some appendix somewhere, negative 635.1. Don't worry, I will give you that appendix. And how do I make CO2? C plus O2 makes CO2, and that's our delta H of formation of negative 393.5 kilojoules. so what do I do to these reactions? All right, so who are my reactants? My reactants is CaCO3, so this one I'm going to flip. So that means I'm going to change this value. So I am going to make a CaCO3 break up into Ca plus C plus 3 halves O2. And my delta H is going to be positive 1207 kilojoules. I'm going to leave these two equations exactly the way that they are. Ca plus 1 half O2 make CaO, and that means I'm going to leave my delta H exactly the way that it is. And C plus O2 make CO2, and leave that one the way that it is also. Okay, so complete it. Add them all up. Squish these three things into one equation. That's going to be CaCO3 plus Ca plus, I have a half plus a 1 right here. So that is 3 halves O2 plus C yields Ca plus C plus 3 halves O2 plus CaO plus CO2. All right, what cancels out? This is my favorite part. I love canceling out because it's so good to make sure that you can prove what you did. I have a Ca on the left. I have a Ca on the right. I have a C on the left. I have a C on the right. I have 3 halves O2 and 3 halves O2. So what does that lead? That leaves CaCO3 decomposes into CaO plus CO2. So if I can manipulate these reactions and get my overall net reaction to be and match my original, that means I can do the same thing to my heats of formation to figure out what my delta H is going to be. And my delta H is going to be 178.4 kilojoules, or an exothermic reaction. So I know this is going to require some energy in order to break apart our calcium carbonate. I'm going to need to heat this up and add this much per mole, or else it's not going to decompose and it's going to stay exactly the way that it is. Now, a little thing to remember is if you have a coefficient out in front, you would have to change this because this is per mole. You're going to have to multiply that by 2. Oops, sorry, it's for this one. So be very mindful of that as well. All right, so to review, all right, we have our calcium carbonate. Our reactions are going to be the Ca plus C and 3 halves O2, making CaCO3. But I have to flip this one because it is a reactance. Reactants get flipped. Okay, because I am not forming it, I am breaking CaCO3. And this is a delta H of formation value right here. So if that's how much it takes to form it, the delta H of breaking, and that's not really a technical thing, would be the positive value, 1207. Your Ca plus half O2 makes CaO, and C plus O2 makes CO2. I'm going to leave these guys, keep them as written, because I do actually form them as my products. And then you put these together by having this one huge complete equation, and then cancel out my calciums on both sides, my carbons on both sides, 3 halves O2. You didn't think those fractions would work out, but guess what? They do, because science. And then you have CaCO3, CaO, and CO2. You get your net reaction. And since you got your net reaction by flipping and adding, I can get my delta H total by flipping and adding. And I get my total value to be 178.4 kilojoules. That is the proof that Hess's law works.